Okay, in this problem, we have this person who has a flashlight, and they're shining the flashlight. So a beam of light is hitting the pool surface. This is a pool. Um, and we know that the flashlight is 1.3 meters. So it's 1.3 meters above the ground or above the pool, the water surface. And the point that it hits is 2.7 meters. So from the edge of the pool to where it first hits the water is 2.7 meters. And it's asking us, where does the spot of light hit the bottom of the pool, measured from the wall beneath the foot if the pool is 2.1 meters deep. So it's 2.1 meters deep, and it's asking us to find from the edge here, from the edge here, where it's going to hit over here. So we're going to measure this distance right here. Okay, so I think it's a good idea to think about how to go about the steps to take for solving this problem. So the one thing I like to do is draw things out just so I have them in my head. Pick blue. So I've got this, and let's say that's my pool, and this is where, right here is where the guy's foot is. Say that's his foot, and right up here is the flashlight, like that. And let's say the beam of light's coming down like this, and I'm gonna my first thing to do with refraction is to make the normal. The normal is like the most important thing because people usually make the mistake and draw the angle with respect to the surface and not the normal. So this is going to be my incident angle. We'll call my incident angle theta 1. And I know when my beam of light, so my beam of light's coming this way, when it hits, so this surface, this is air, so this is n equals 1, and this is water, so this is going to be n equals 1.3. And I know whenever light goes from less dense to more dense, it bends towards the normal. So I'm just gonna like exaggerate that. So this right here is going to be my theta 2. And so I know that this distance right here is 2.7 meters, and I need to find this distance and then add them together. So the first thing I want to do is I need to figure out, so let's just write down our steps. So 1, I need to figure out theta 1. So what's theta 1? And I can do that by, I'm given information about my triangle, right? So I know this is 2.7 and this is 1.3. So I can make a little triangle here. And I can figure out this is 2.7 and this is 1.3. And I can figure out this angle by using tangent. So I can say tangent theta is equal to 2.7 over 1.3. And figure out, and then do inverse tangent to find my theta 1. So we'll call this theta 1. So what's theta 1? That's my first thing I'm going to try to solve. So the next thing to do is once I have theta 1, then I need to calculate theta 2. And this is theta 2, right back over here. My theta 2, the angle that the beam of light enters the water. Next is I need to find x. So find x. And I can use trig in my new angle that I just calculated, and theta 2. And then the last thing I'm going to do is I'm going to add 2.7 plus x gives me the distance. So that this will give me the answer to my problem. Okay, so let's figure out what my tangent is. Okay, so we're going to calculate our angle here. So that's the first thing we're going to do. So we can say our theta 1 is equal to tan inverse of 2.7 over 1.3. And therefore we get an angle theta 1 is equal to 64.3 degrees. Okay, so next we need to calculate theta 2. So what we're going to do, we're going to just switch to the next slide. And So in order to find theta 2, remember we're just doing this. We got our normal. We know this is our theta 1. This is our theta 2. So right in here is our theta 2. And so we're going to use Snell's law. So Snell's law says n1 sine theta 1 is equal to n2 sine theta 2. We know theta 1 is 64, so we're trying to find theta 2. We expect it to be smaller. So this is what we're solving for right here, theta 2. So how are we going to do that? Well, we're going to divide both sides by n2. So we're going to have n1 over n2 sine theta 1 is equal to sine theta 2. And so we can plug in here. So we have 1 over 1.33 sine of 64.3 degrees. And when we work that out, that gives us our sine 2 or sine theta 2, which is 0.66. So that tells us then, if we do the math, that theta 2 is equal to 42.6 degrees. And that makes sense because we know that this is 64, theta 1 is 64, so theta 2 has to be less, so 42.6 makes sense. Our next step is finding x. So remember, I go back over here and I extend this out a bit more. This is our x. So we're going to try to find that. And so we know theta 2. What we can use is we can use theta 2 and calculate x using tangent again. So we're going to say now we're going to do opposite over adjacent. So tan theta 2 is equal to opposite of this angle is x divided by this height is 2.1. So that tells us that we have x is equal to 2.1 times tan theta 2, which is equal to 2.1 times tan of 42.6. So x here is equal to 1.9 meters. And so then last thing we have to do is, if we just go back one slide, well, we'll just draw it out here. Remember, we are trying to find the distance back here to the edge of the pool. Right, and so this right here is the edge of the pool, and this was equal to 2.7 meters. So let's call this L. We're trying to find this length to here from the edge of the pool. We'll call that L. So L is equal to 2.7 meters plus X. And when we plug in 1.9, we get L is equal to 4.6 meters. And that's our answer.